Welcome back to GATE XAML. So today we'll start the new chapter, the basic probability theory. So there are a few terminologies we need to understand, and some simple examples to begin with, and then we'll see the advanced problems. Okay. So let us understand what is random experiment first. A random experiment is a process or action that leads to one of several possible outcomes, where the outcome cannot be predicted with certainty in advance. What it means, when I toss a coin, so it's an experiment I'm conducting. The experiment will produce you the data, that is outcomes. So tossing a coin has two outcomes, either it's a tail or it's a head. Similarly, rolling a die, it's an random experiment which has 6 possible outcomes. It has phase 1, phase 2, phase 3, phase 4, phase 5 and phase 6. So 6 phases. So similarly, drawing a card from a deck, measuring the temperature on a given day. So any experiment that you conduct which has certain outcomes is called as a random experiment. Next, the next concept is a sample space. Okay, once you conduct the experiments, then you get the outcomes. So outcomes form all the outcomes that come from an experiment, random experiment, forms a sample space denoted by S. For example, say that tossing a coin. Tossing a coin has two outcomes. It is head or tail. So the sample space can contain head as the outcome and tail as a outcome. Similarly, rolling 6-sided die. So the outcomes will be 1, 2, 3, 4, 5, 6. That is a die of phase 1, 2, 3, 4, 5 or 6. So similarly, tossing two coins. If I toss two coins, okay, the coin 1 and coin 2. So what are the possible combinations? You may get head here, head here, head here, tail here, tail here, and head here. Then tail here and tail here. So possible combination sample space is what? So all the possible combinations will form your sample space HH, HT, TH and TT. This is the concept of sample space. So you understood what is a random experiment and sample space. Now we will define an event. An event is a subset of a sample space. It consists of one or more outcomes of the experiments. Suppose say that what is this event in the previous example? Okay, so you have 6-sided dice, okay, faces. So say that what are the possible, what is random experiment there? Random experiment is that tossing a die, 6 faces die. What is the sample space? S is equal to, you can get 1, 2, 3, 4, 5, 6. Okay. Then what is the event here? Let us denote it by E. Event is nothing but, see, outcome 1 is a event, 2 is a event, 3 is a event, 4 is a event and 5 is a event. That means, for example, if I say getting 3 on tossing a die, so it's an event. The event can be any one of the sample space. Okay. So there are different types of events. Simple event contains only one outcome. Getting a 4 when a die is rolled is the one outcome. So this is one simple event. Compound event contains more than one outcome. So if I say that getting a even number die, so that is you need to get 2, 4 or 6. These are the even numbers. This is a compound event. Certain event means the entire sample space getting either 1, 2, 3, 4, 5 or 6. So it is a complete entire sample space a certain event. What is the impossible event? The empty set never occurs. For example, if I say getting 7 on a die toss is not possible because 7 is not there. So it's an impossible event. Next, we'll try to understand the concepts of random experiment, sample space and event. We will now define the probability. What is probability? In general, we say chance of occurring. Okay. Probability is a measure of likelihood or chance that a particular event will occur when a random experiment is performed. So throwing a die, okay, is a random experiment. Now getting even number is a event that I want to observe. So the likelihood of getting that even number die on a die rolling experiment is a probability. This is how you define. So probability is always between range from 0 to 1. So 0 to 1 both included. So 0 means that event cannot occur. Okay. 1 means it will occur with certainty. So values between 0 and 1 indicate degrees of likelihood. What is the percentage chances that this may occur? For example, occurring of a head in a coin toss. So head is one event and total sample space contains 2, that is head and tail, right? So the likelihood is 50% or 0.5. This is how you write the probability. So now, to every point in the sample space, a probability or weight is assigned such that sum of all those probabilities is equal to 1. So what I mean to say, if I use the same experiment, tossing a die experiment. So what are the outcomes? The sample space can contain 1, 2, 3, 4, 5 and 6. Now each one is an event here, okay, occurring of 1, occurring of 2, occurring of 3, like that. So the probability attached with this is occurring of 1 is 1 by 6. Okay, just like probabilities of each of events. Occurring of 2 is again out of 6, 2 is 1. So 1 by 6, all 1 by 6, right? So uniformly distributed. So what it says, so this is the probability of each of the events, whatever written here. Now, so if I add all this, surely I'll get 1. That means sum of all the events in your sample space will be always equal to 1. That means what? Every point in the sample space is attached to some probability value or weight. See, 1 is attached with 1 by 6 weight, that is probability. 2 attached with 1 by 6. If I add all this, then I should get 1. We will get 1. So same example they are given here. So let the sample space be S equal to 1, 2, 3, 4, 5, 6. Each outcome is equal likely. So P1, P2, everything is 1 by 6. Previous example that I have written, I have shown you. So let A be an event. Okay, there is an event. It's a compound event which says that getting an even number. See, out of 1, 2, 3, 4, 5, 6 spaces, 2, 4, 6 represents the even number. So getting this is what? I can get even means 2, I can get 4 faced or I can get 6 faced die when I conduct the experiment. So the outcome is the sum rule, right? 2 or 4 or 6, only one outcome can occur. What are the ways? So 2, one way, so 1 by 6, 1 by 6 plus 1 by 6. This is how calculate the probability. Example 2, impossible event. So I have told you already. If B equal to 7 when tossing a fair die, because tossing a fair die, the outcomes are what? 1 to 6. There is no 7. So probability is 0 because the event B does not belong to sample space S. Next is a certain event. Let C equal to 1, 2, 3, 4, 5, 6 be the event. Any outcome occurs. Any outcome means any one of these occurs. So P1 can occur, P2, P3, P4, P5, P6. Probability of this is 1 by 6 plus 1 by 6. It will be 1. So that is a certain event. So you can also define probability in another terms. Okay. Yeah. Whatever probability definition I am explaining till now, and this one is a discrete probability definition. Okay. So I don't want to explain now the continuous probability distribution because you will be confused. Let us start with this. When I explain the continuous distributions, I will explain the actual probability definition. This is not actual probability definition. So you can also define it as numerator by denominator. Think probability is numerator by denominator. Okay. In the numerator, what is that you will take? Number of favorable outcomes for event A. Which one you are favorable with? That means, for example, getting 2 on the dice. Okay, that is an event. So that how many can occur, that we represent by n, and total number of outcomes by capital N. So in that die example, occurring of 2 is one way, divided by n is total 6 outcomes, 1 by 6. That is how you define the probability. I will take a simple example. A website displays 10 advertisements based on data collected from 2500 visitors. In that, 30 visitors clicked one advertisement, 15 visitors clicked 2 advertisements, 5 visitors clicked 3 advertisements. Okay, this is the data given to you. Now, what remaining visitors did not click on any advertisement, remaining all those out of 2500. Now, they are asking what is the probability that a visitor will click on an advertisement. So, click on an advertisement means at least one advertisement they have to click. So, that is nothing but this 30 visitors click 1, 15, 2. That means at least 1, right? 2 means. So, 5 visitors, so greater than 1, greater than equal to 1, so 3. So, we will add all those them. So, total at least one visitor, at least a visitor has clicked one advertisement, that is 50 visitors are there. So, out of 2500 is a denominator, 50 have clicked at least one advertisement. So, this is the probability. Now, what is the probability that a visitor will click on at least 2 advertisements? Visitor who clicked at least 2 means what, which cases will come? This is at least 2, this is at least 2, no? So 15 plus 5. So 20 visitors have clicked on at least 2 advertisements. So this is the probability, 20 by 2500. Now, see, what is the probability that a visitor will not click any advertisement? See, total we already got that 50 users click on at least one advertisement. Okay. So that means remaining 2450 do not click, no clicks. So that means out of 2500 to 2450 have not clicked. So this is the probability. Next, so we will see some of the probability axioms. Okay, what is an axiom? Axiom is a statement, okay, which is already been proven or established. Okay. Any statement which is established or well proven. So first axiom of probability is non-negativity. What it says, very simple. So probability cannot be a negative value because it lies between 0 and 1. That is what is the first axiom. Second axiom is normalization. That is, sum of the probabilities in the sample space is 1. That is already you have seen, right? Sum of all the events in the sample space is 1. Then is next one is the additive. For any two mutually exclusive, okay, don't worry about this mutual exclusion. So they are disjoint, means A and B occur separately, like your sum rule if you remember. So both cannot occur together. Then those events are called mutually exclusive. The next shortly I will explain what in detail what is mutual exclusion and how to identify the problems containing mutual exclusivity. So for a mutual exclusive events A and B, P of A union B is given as P of A interest A plus P of B. Okay, more on this later. Next, let us see some example. Let the probability of rain be tomorrow be P of R equal to 0.6. So it is non-negativity. That axiom 1 is satisfied. Normalization. You already have seen this. Suppose a fair die is rolled. The sample space is 1, 2, 3, 4, 5 and 6. So if you take attach probability for each of the sample space events, then the sum will be equal to sum of all will be equal to 1. Sum of all probabilities, right, like this, the sample space equal to 1. Next, additivity. Let A equal to getting an even number when a die is rolled. That is, A should be 2, 4 or 6. Let B be getting an odd number, that is 1, 3, 5. See, they are both mutually exclusive, right? That means what, they are disjoint. It cannot happen like you'll get 2 and also and you'll get 1 also. It's not possible, right? You'll get only one outcome when a experiment is conducted. So they are mutually exclusive. So P of A getting even is 3 by 6. Because 3 numbers are even, 3 numbers are odd. So total probability is 1. Next, you'll see some of the rules of the probability. This may also again include some of the axioms. For any event, the probability is a number between 0 and 1. This already you know. Next, sum of all probabilities is equal to 1. Next, probability of an impossible event is 0. That is what I given the example, right? Beginning. Rolling a 7 on standard die. So 7 is not possible, so it is 0. Probability of certain event is 1. That means if all the outcomes, if all the events of the sample space are asked, then a certain event is going to happen. So for example, tossing a coin, getting either head or tail. See, there are only two outcomes. Both the outcomes are expected, head or tail. So it will be equal to getting head is 1 by 2, getting tail is 1 by 2. So it's a certain event. Complement rule. Complement means what? You subtract from 1. See, what is that they are saying? This is how you have to imagine. More problems will solve in distributions. So this entire thing, we assume this probability as 0, 0 to 1. Now they are saying that P of A, somewhere they are saying this is say 1 by 3. Okay, this is a event A and this is event B. So probability of A is 1 by 3. How will you get the probability of B? Probability of B will be 1 minus A, probability of A, right? It is 1 minus 1 by 3, this part. So this is how you can solve the problem. That is the complement rule. Next, we'll understand now in depth what is this mutual exclusive events. The two events A and B are said to be mutually exclusive or disjoint if they cannot occur at the same time. That is, their intersection is 0. If you draw a Venn diagram, so this is a event A, this is event B. Okay, they cannot occur together. If they occur together, there will be intersection part. Right? There is no intersection part. So this is B. So here, if we say intersection B is equal to 0, that is, to attach a probability P of intersection B will be 0. Such events are called as mutually exclusive events. That means both cannot occur. How to identify? If two events describe outcomes that cannot happen together in a single trial of the experiment, they are mutually exclusive. We'll take an example and understand. Tossing a die. We let A equal to getting a even number. Let B be a even getting odd number. Okay. Now say that if you draw the Venn diagram, let us this is A, this is B. A is contains what? 2, 4, 6, all even numbers. It contains 1, 3, 5. See, there is no intersection here. So that's why these two are mutually exclusive. Okay. Now there's one more thing. Many students confuse here in the problems when they are given how to identify mutually exclusive and independent events. The mutually exclusive means you just understand in a single experiment you cannot have both the occurrence. A and B cannot occur together. Then it's a mutually exclusive. Two events A and B are said to be independent if the occurrence of one does not affect the probability of the other occurring. That is, P of A intersection B is equal to P of A into B. This is, if you remember in our combinations, this is something like product rule. Previous one is like a sum rule. Both cannot occur together. They can occur in a sequence. How can you identify? The question says the probability of one event is not influenced by the outcome of the other independent, then they are independent. Example, if you see, let us take two events. One is first a coin shows head. Okay. Second coin. So there are two coins. Okay. The first coin shows head. The second coin shows tail. See, the occurrence of head for this coin is independent of this coin. Okay. They are not dependent. So if P of A equal to 0.5, P of B equal to 0.5, then P of A intersection B will be equal to P of A into P of B. Similarly, similar example, rolling a die and tossing a coin experiment. See, I will roll a die and I will toss a coin. So both are independent experiments, right? So there is no intersection here. Okay. One does not influence the other. The probability of getting A is equal to 1 by 6. Probability of B is equal to 1 by 2. Both can occur independently. So P of A intersection B is P of A into P of B. Is probability of A into probability of B. And they are independent. So how to identify problems? See, mutual exclusion, check if events can happen together. If not, they are mutually exclusive. Can they happen together? Independent means compute P of A intersection B and compare it with P A into PB. Once you solve the problem, you'll understand. If equal, then events are independent. One more thing, the mutual exclusive events are never independent. Why? The mutual exclusion means they cannot occur together at all. So one of them should occur. So unless other probability is 0. If other is 0, the probability itself will be 0 because P of A into P of B. The next one is the addition rule for mutually exclusive events. When I add this part P of A intersection B, the P of A union B, you already know the formula, right? P of A plus B of B minus P of A intersection B. You already seen that mutually exclusive means this value will be 0. Next, rule 7, addition rule for any two events. So they are not saying mutually exclusive events, they are saying any two events, can be any two events. Then in that case, you have to subtract this intersection part. In beginning of combinatorics, I also explained this. This is what they are saying. This is A, this is B. So this is the intersection part. So this is counted twice, right? Here also it is counted, here also it's counted. So let us take an example. In a class of 40 football, if they play football, 30 play cricket and 10 play both. Okay. So 40 play football, 30 play cricket and 10 play both. So total there are 100 students. So now the denominator in probability is always 100. A union B you have to find. Okay. How will you find A union B? 40 play football, 40 here, then 30 play cricket, then 10 play both. So that means you are counting 10 two times. So 40 football, cricket minus both. So that will be 0.6. Now multiplication rule for independent events. So already have seen it. If the two events are independent, then P of A intersection B equal to P of A into P of B. Same examples you have seen. So you learned basics now. So in the next class or next video, we will see the most important fundamental concept of probability theory, that is conditional probability, and then the Bayes theorem. And we'll solve many examples and then we'll solve previous gate questions. Thank you for watching. Please subscribe, like and share. We'll continue in the next video.